I'm really happy to present the analysis, an update concerning the. I have to say that the most exciting scientific thing in my whole career. I'm not sure what it means to you, but to me it really means a lot. And of course, this is not an argument. I'm going to present scientific arguments that support this excitement. So in particular, I will argue that what we know as cosmo-seismic correlation effect, which has been published, you probably know this article, you know the reference. If not, please click. You have the slides. You can also jump forth and back if you want. So it's all on the website. And this particular effect is statistically significant. It's confirmed independently in many ways. But the problem is that we completely do not understand what is physics behind. So in particular, we rather do not see a causal relation. So it's not like cosmic rays induce seismicity or earthquakes induce changes in cosmic rays. It does not look like that. So a collection of weird, so to say, properties of the effect really point to an exotic explanation, because we do not have conventional candidates. So that's only why we go for exotic alternatives, which you have in the title, charged dark matter. So not only dark matter is already something, but it's not enough, at least what I can see in the data. We need something, not necessarily dark matter, of course, but it might be something, whatever, that is active both gravitationally and sensitive to magnetism. So I'm going to give arguments. And of course, please don't mind the introduction. I mean, despite it's very, very exciting for me, it should not block your criticism, just the opposite. You are welcome to really criticize as much as you like. We are here, this is internal meeting, we are here as a family. So we can really jump on this and on me. If we find a conventional explanation, it's also great. We just want to understand what we see. So this is the article for the CREDO collaboration. So many names, including amateurs. So this is, we are proud of having people who are not fully trained scientists on board. They are really active. They really help in delivering results. And the significance of the effect is on a discovery level, actually. So we might say that this effect is maybe the first thing that CREDO produces that says something new about how world is working. So it's something new. If you believe in the article, because it's not that easy that you publish and the world is accepting. It's not like that. Despite the state-of-the-art methodology, despite independent cross-checks, there are still many colleagues who simply do not believe that there might be any relation between cosmic rays and earthquakes, because it's hard to imagine. What could it be? But let's be optimistic. I'm going to briefly review the article first. So these are our data, cosmic rays at 3 locations. The 2, Moscow and Oulu, from Neutron Monitor database, and the other one, red dots, represent the data from the Piotr Observatory, the public data. So you have 3 different locations and 2 different technologies. This is important. And in pink, you have earthquakes. It's specific observable is this magnitude sum of the earthquakes binned in 5-day bins. This is important. This is one of the magical numbers in the article, 5-day bins. Please keep in mind. And you see, okay, here is here is on the left, you see the recent data, so to say, last 2 decades, and on the right panel, you see a full picture of the data we have, compared also to solar activity in yellow. You also see this dramatic drop in earthquakes around to 1972, which is due to some technological circumstances. Simply before that date, lower magnitude earthquakes were not recorded at all, or not that efficiently as later. You also see some trend in earthquake data, which is actually not clear. Maybe it's some physics, maybe techniques, but if it is techniques, then it's gradually improving, so to say. So we have contacted the source, USGS, and they do not react to this question. So we take the data as it is, and we hope, nevertheless, the statistical significance is valid. What is also important, that we are checking specific observables. As I said, this is the sum of the magnitudes of earthquakes above magnitude 4, and we also check how it compares with absolute changes in cosmic ray detection rates. So you will see the explanation in the next slide. So we have 2 data sets, cosmic rays, CR, earthquakes, EQ. We divide the sets into 5-day bins. We shift one set with respect to the other by 15 days, another magical number. We check some number of the bins, which is quite a long period. It's 4.5 years or 9 years. We have 2 versions. And for this configuration, we compare the data bin to bin. So each first bin with first bin, and so on and so on and so on. So if we have 335 bins, we have 335 comparisons. For each pair, for each set, we calculate the median, so half of the values. So half of the bins is below the median, half is above, roughly speaking. And then we ask what is the distribution of coincident signs. So if you have above and below, then if you compare with another set, you might have above and above, above and below, below and below, below and above. So 4 options, like throwing a coin, and it should be equally distributed. So roughly speaking, 25% for each option. And if you consider plus plus and plus minus separately, so you have only 2 groups, you should have 50-50, which is described by binomial distribution. So this is really basic math from high school, binomial distribution. Maybe use Mike, because we...
Excuse me, how do you know which bins to compare?
This is the common starting time. The common starting time defines where we start looking, except this shift. One data set is shifted with respect to the other one by 15 days. So when to start, what is T0, I will show in the next slide. So that's of course important, because we know that the effect is dependent on time. So this plot shows T0 row. Let me explain. So this 3 colors is the chance probability for having unusual number of, I should maybe clearly introduce, n plus is the situation when the value of a bin is larger than median. in one set and in the other, or if both are lower. So plus plus or minus minus, this is n plus. And the other n minus is when one is larger and the other is lower. So these are the options I have mentioned. So if n plus is similar to n minus, nothing special can be seen. But if one is significantly larger than the other, then the chance probability, this PDF function shows this. So the lower chance probability, the stranger the result. And you see this strangeness here because you reach really low numbers for some t zeros. It's not everywhere. 3 locations. Again, we have 3 locations for cosmic rays. So we check local cosmic rays, local, and compare to global seismicity. This is an important distinction, local versus global. And please see that for the 3 locations, we reach very low numbers in terms of chance probability. So it's unlikely to happen by chance that we have a symmetry of n plus and minus numbers. And this plot is specific because it shows last 4.5 years. So last 335 beans. So for instance, here at 2016, we can say that last 4.5 years is boring, right, in terms of the effect. But please note, we compare with solar activity that at that time, last 4.5 years is a very active sun, right? So, and we have nothing here. We only begin to see the cosmo-seismic effect, I mean the asymmetry between n plus and minus, later. In the solar deactivation, I don't know the word, when sun becomes less active. And you see, here we reach 10 to minus 10, which is more than 6 sigma, but it means nothing statistically because we have manipulated the parameters. We did manipulation inspired by many factors, and we derived something. But this is not statistically insignificant just because this manipulation, you cannot determine the penalty factor. So this has to be considered a burning sample. We have to disregard the sample and check our prescription in other data sets, maybe earlier data or elsewhere, whatever, not this data. So this is just an illustration that this kind of configuration of the parameters I have mentioned, this dichotomic correlation, might be an idea for a prescription only. And importantly, you also have this 15 days precursor effect. So you need to shift everything, otherwise you do not see an effect. So you need to shift, in this case, it's really one direction. So you shift 15 days, you need to shift the cosmic ray data 15 years forward in future. So you compare cosmic ray data today with future seismic data taken globally. And you see that if you check which shifts produce which effect, this is just one example, one data set. So this is just an illustration. But please see this very sharp peak. And on the left, when you shift the other side, it's nothing. And on this side, where the cosmic rays serve as precursors, you have very sharp peak. Maybe there is some additional structure. This has to be investigated further. And what we finally get, this is the final figure from the article, is this plot. So this is our burning sample on the right, which helped to define the prescription. And this prescription gives other peaks in the past. So we have 4 distinct chance probability functions, chance probability function minima in the past. And the probability of having these 4 distinct minima gives us the 6 sigma effect. I see Marius wants to say something. Marius?
Hi, Piotr. A really quick question, actually. Hello. A really quick question about the earthquakes that you used over here. Did you use all earthquakes regardless of the magnitude, or did you take like the higher magnitude ones?
We have a threshold of 4, which we apply to our data. So all
Sorry, I missed
I'm
this.
discussing here and in the article is the threshold of 4.
Above 4, then.
Above
Okay.
4, I don't know. Maybe I have not mentioned. I'm very sorry about that.
No, maybe I missed it because I was not there in the first slides. Okay.
Oh, it's only it's hidden here. It's hidden here. Sorry, thank you for pointing out.
No, okay, thanks. Because we also saw these kind of significant results above, like in very high energetic earthquakes as well. So
yes, we've discussed this.
we have discussed this in the past.
And Marius, maybe in the discussion part, you could say a few words. Marius has important results for slightly larger magnitudes, larger than 5. Very interesting ones, actually inspiring.
Yeah, thanks, Piotr.
Let me continue with the final figure, but only larger time window produces so clear picture. So the blue curve is 9 years, no, not 4.5, which is 335. It's 770 beams, which is nearly 10 years, 9 years, which produce a clear structure, which is the final sigma number. And also, please note the shift with respect to solar maxima, which are indicated in the other color. So this is our strange result, our weird result. Already, as in the article, sorry, it's outdated. It was for quite a time. It was only an archive paper. So what is the interpretation? What can be the interpretation? Is this periodicity reflecting the solar activity? Or maybe, as we will hear in the afternoon, maybe it's not really 11 years cycle, maybe it's lunar cycle. So Mikhail Kovalyov contacted us after the article was published, and he pointed out that the gaps between the peaks are on average 10.2 years long, not 11 years, 10.2 years, which by chance or not corresponds to the periodicity related to coincidence of the perigee point and new or full moon position. So it's the alignment of sun, moon, and earth, which is a special point, and the minimum coincidence where they really coincide with perigee point, where the moon is closest to earth, happens every 10.2 years, like here. So we are working on that. It's not clear whether this minimum syzygy or maximum, as you prefer, corresponds to these peaks, because we have white windows. We do not have an effect which appears only once per 10 years. We have wide windows, and only considering these large time periods gives us this result. So it's not clear if this is really corresponding to what Mikhail is proposing, but at least the coincidence of the numbers is striking. 10.2. Okay, so one of the speculations is already on the table. And now I'm going to to begin the longer list of speculations. So I'm listing here only selected peculiar properties of the cosmo-seismic effect. I hope to have time to go through the first 4. And I'm going to argue that these peculiarities could at least qualitatively be explained by something which is sensitive, something, I don't even say dark matter, something which is gravitationally active and sensitive to magnetism. So let me start with the first property, which is a sensitivity to the starting point. So you remember that we work with wide windows, 9 years or 4.5 years. And T0 is the starting point when you start to count the beams. So you start, for instance, today at 12, and you count beams next 9 years. So this T0 turns out to be a very important parameter. And I'm going to explain this in a few slides. So here you see n plus and n minus numbers for another location, not Pieroge, it's Oulu, it's Finland. We have cosmic ray data from there, it's public, and we use data which are binned in 6-hour bins, so 6 bins per day. And maybe I will come to that. We use slightly different bins, not 5 days sharply, but slightly less. Maybe it's 1/9 too much. It's 9/9/9/15. Sorry about that. And you see the evolution of this n plus and minus asymmetry in time. So we have big windows, but we have sliding average with a very small step, 1 hour. So again, the windows are big. I think it's 4.5 years. And you see that it's not always like that n plus is very larger than n minus. So it might be the opposite. And it's evolved, it's dynamic. So it's not at all a constant effect, not at all steady in time. So you have a zoom of this maximum region. So you see the number here, it's 10 to minus 14. So it's far lower than the minimum from our burning sample. So it's another manipulation, of course, but we have another location, another bin, but the effect might be even that significant, 10 to minus 14. And now see the zoom, see this structure here, which will be enlarged even further. So you have only 20 days here. So there is a periodicity of the length of 5 days, like the bin, but only one particular position of T0 within this bin gives a significant effect. Only one particular position or very sharp position of T0. So you see we have periods of 4 or 9 years. We shift by 10 minutes our starting time and we lose the effect. So super fine sensitivity to T0. So whatever professor or student, the first impression is this must be technical. No way to explain this kind of effect physically. Okay, maybe that's the case, but we have checked many times. You are welcome to do yourself. And we have an idea how to produce such a sensitivity physically. So I'm going to argue on that. But before I do this, please note, so only one maximum. Here we have maximum because we deal with n plus. So large n plus compared to n minus. If we have we have 4.5 years bins, so 335 bins. If we have 230 n pluses, it means that we have, as you saw on the previous slide, that we have around 100 n minuses. So it's really large asymmetry of the binomial distribution. 230 versus 100. But it's not always like that. But at least within some time, okay, it's clear why it goes to the same values when you shift by the bin size. Just because when you shift by bin size, you only lose 1 n plus or 1 n minus. The difference cannot be large. But if you shift by a fraction of a bin, a difference might be dramatic. And here you see the largest zoom. So the very peak here. So you see that the shift by this is very small steps here, small sliding step. The periods are still large, 4.5 years, and you have something like 10 steps here. When you go from the maximum, you lose 15 bins, 15 n pluses, dramatically, and even more there. Okay, But remember, we have 6-hour binning in cosmic ray data. So this kind of effect is then likely to come from the earthquake data. That's maybe a hint. And another thing, not included in the article, is that this T0 parameter, which is a kind of universal parameter for each site, which might be applied to the whole data set also in the past to give a significant result, it turns out not to be so universal. Because if you compare this optimum T0 in one period of time to the value optimum for another period of time, you have the optimum point at another location. So it's not universal, it's changing. So what could it tell us about the physics? So it's important that this evolution might be really a clue. And as I said, earthquake data are suspected. And now the idea very, you might consider it's too naive, but whatever. So that's my artist's work for the explanation, possible explanation, how it can be organized physically that we have such a sensitivity for large windows. So I will be clicking back and forth. So you see a specific signal in cosmic rays, which has maxima which are more or less regular. So the maximum should repeat regularly as our binning. So not necessarily in every bin, but in binning should be corresponding to the signal maxima. So we have 5 days. So this should be something which repeats after a multiplicity of 5 days. So something like that. And on the other side, earthquakes should have not a similar shape, but something which has also a drop immediately after the maximum. In this picture, you have plus here, plus here, plus here. You might have it in many places. So you might have n pluses distributed over your white window. But if you shift the bin only slightly by, for instance, half of the bin, you might lose the effect globally because you lost only half of the signal in cosmic rays, but your maximum in earthquake data might be totally compensated by the minimum which is coming shortly afterwards. So you might have 0 here, and then you don't know what you have, plus or plus minus. So in this way, a very tiny shift of T0 might give you a global effect, global in the sense of the window size. So just please think a while. So how can we be sure a priori that such a signal is unrealistic? Just the opposite. We seem to see such a signal in earthquakes. And this is my second argument. So the first argument is maybe not really referring directly to dark matter scenario. It's just pointing to a very strange, peculiar property of the effect, which might give a clue about further considerations. So now we are focusing on earthquake data. And the keyword is a 24-hour periodicity. So what you see here, it's not magnitude sum anymore. It's just the number of earthquakes. This is preliminary work in progress, so please excuse imperfectnesses. What you see, it's an average day in earthquakes in some period, 2000 days since 2014. Some specific period, again, manipulation, you can say, but please think about it a while. So we have 1-hour bins. We do sliding average, as always, to see better the behavior. So if you want independent values, consider just 1-hour binning. But small sliding step shows you the features. And what you see is that at 6 a.m. UTC, you are the safest. Because there is a clear minimum in earthquakes globally. Okay, you might complain there are no error bars. Yes, I agree, but this is hard to provide error bars. Okay, you might propose Poissonian error bars, but that's not reflecting physics, because earthquakes are clustering. You know that after big earthquakes there are many aftershocks. There are also pre-shocks sometimes, interestingly. So it's not easy, but I will going to argue why. Okay, if you consider Poissonian noise, it is already clear that it's significant. Also by eye, this drop is strange, this is strange, this very sharp peak is strange. Okay, but this is not science. The strange is not science. For now, I want you to remember the shape. So it does not look like flat. It has features. So we might consider time evolution of these features. If this is, for instance, induced just by one major earthquake and numerous aftershocks, or maybe this difference is only random, we can see by following temporal evolution of two places, for instance. But I should also add here that this periodicity of 24 hours is, of course, also seen elsewhere. If you consider periodograms, for instance, you see this. This is a major component in periodograms. I'm talking about Lomskargel periodograms here, or Fourier analysis if you prefer. So dominant factor, this asymmetry is also seen elsewhere. What is also very important for this talk, we do not have this lunar day periodicity. Lunar day is when a certain location meets moon at the same position. So moon, of course, as you know, is moving, right? And we might come back to the same position versus the moon after 24 hours and 50 minutes. So it might sound similar, but it's not. It's very far away. So 24 hours asymmetry here. I'm not showing, sorry, but I will give an argument that should convince you. No lunar day periodicity, or weaker. For sure, this is dominant from all I have found so far. Dominant 24-hour periodicity, no lunar day periodicity. And the number, the 24, points to the sun. What else? What else? 24-hour is the time where a certain location is at the same position with respect to the sun. Okay, you might suspect gravity, because of course Earth is not uniform, and some seismically active region is at the same position with respect of the sun every 24 hours. That's trivial. But then, if this is gravity, why this is evolving? I'm going to show how this is evolving. And now the evolution. As I said, you might suspect this is a single effect, but if you follow the evolution of two particular beams, here I'm not consider 1 hour beams anymore. To be even more precise, I'm considering 15 minutes beams. So you consider the difference of the earthquake number in 15 minutes, beginning from 6:45 to 7 p.m. UTC, and you compare to 15 minutes 12 hours later. So take these two beams, right? So this is corresponding to peak at the 6, and at 12 hours later it's here. So these two positions. So what you see is evolution. So nothing, maybe at 2000 something, and dramatic drop at 2014. Dramatic. Something is happening, the asymmetry grows. But what you for sure agree with is that it's not flat. Do you agree? It's not flat. So how could it be explained with gravity? And another thing, in different periods, different times during the day have this dramatic effect, which is indicated by this blue line here. I will not go into details. So there is significant evolution in time. And if you zoom in this dramatic period, you see that the increase of asymmetry is not at all associated with single earthquake events. It's increasing gradually, more or less, although it is not smooth. So who knows what single sharp peaks could mean here? But it's not one event for sure. It's also hard to see yearly periodicity, but it's regularly increasing within 5 years or so. And here, the evolution of this asymmetry. So now you just compare another binning here. Sorry, it's 3-hour binnings, but we are with daily averages. We are with 24-hour asymmetry, and we just ask what is the minimum bin to average bin. So it is kind of a measure of the asymmetry. And we do sliding average, but with big steps. So that's why this is not smooth. So you see the asymmetry is large here, then it goes away, then it's large here, it goes away, and again, and again, and again. And I cannot guarantee for this region because the number of earthquakes here is not corresponding to what we have in other locations in time. So you see, this asymmetry changes in time, and this is it's focused around 24 hours. So you might now think whether it is an argument for you that we have something which induces earthquakes, but which is sensitive not to solar gravity, or not only, but mainly to other properties of the sun, and one can think practically only by magnetism. So this is what the sun is having, and this magnetic field of the sun is affecting everything in the solar system, because we have solar wind, we have emissions, and so on and so on. So if not gravity, then what? Evolution in time. The third argument relates also to what Michał is proposing. I mean the gravitational explanation only. So if we have some alignment of the planets or the moon only, then there might be some effect. Tidal forces, right? It might also correspond to this mysterious 15 days precursor, which is half of the lunar period roughly. So a simple plot showing the number of earthquakes with respect to the moon phase already tells you that if there are tidal forces, then they are much weaker than something else. And this something else, I don't know what, is illustrated here. So you have moon phase on x-axis. 0 is new moon. So moon is blocking the sunlight. So it's between sun and the earth. 180 is full moon, so on the other side. And quarters are at 90 and 270. Again, hard to argue about the error bars, but you might consider simple Poissonian sigma. So to me, again, this is not flat, but please complain if you think it is flat. And we have one clear minimum, surprisingly, at new moon. So tidal forces are expected to be largest at new moon or full moon. That is what we know from the water tides. Largest effect at new or full moon, because then the forces are strongest. And we showing this dependence of earthquake number on moon phase, we see minimum at new moon, and at full moon maybe something, but not the optimum, not the maximum of all times. Another thing, but I don't argue about it, is that maybe we see something at the quarter. So it's like the moon is on the way of the Earth. So we see Earth is traveling and the moon is just on the way or behind. But the number of maxima here is larger. So we have many peaks. What could it mean? But The message from this plot, the argument from this plot, is that the earthquake number versus moon phase is not flat and it has a minimum. So to me, it tells us that we have some role of the moon, but not gravitational. It might be gravitational, but this gravitational role cannot be related only to the mass of the moon. So, for instance, moon might serve as an attractor or modulator of some external, whatever it is, fluid or stream or whatever, which is gravitationally active and which might produce some effects on Earth. So no tidal forces. Sorry, Mikhail, if you hear us, I'm really opposing. Maybe there will be a discussion in the afternoon. How it evolves in time again. How it evolves in time. This is an easy check. So we might compare this minimum. If you want independent beams, it's 0 to 10. So shortly after the new moon. And another beam, the first local maximum. Very nearby, only 30 degrees. So you see the difference. Again, maybe something is happening here, then flat, 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 flat. Oh, 2000 is shifted, sorry. 2000 should be at 0. Something at 2000, and again, dramatic period at some point of time. But this is not the same period which you have seen before. It's another period. But only sometime. Sometime, it's 5 years again, but different 5 years. Flat, flat, flat. And maybe something is happening right now. So this is about the role of the moon. The role, what properties the moon has? Mainly mass. Not really magnetic role. You have the zoom here. So again, not a single event for sure. You have some jumps, but in principle, it's gradually increasing. And you have, for instance, this particular part enlarged even more. So it's discrete just because we compare not full moon range, not full moon phase range. We just compare two beams, which means that you plot the difference in this part. Only it can only increase just because we count only events from where the moon phase is 0 to 10. And here the other line, they are separated. The other line shows the number of earthquakes in another moon phase beam. So that's why we have discrete plot here. And you see that the other phase range is having larger increases globally during 5 years. So something dramatic is happening. We don't know what in a narrow period of time, not in a whole history. So my fourth argument is related maybe closer to what Marius was doing. So it's about periodicities. We already know that looking at periodicities around 24 hours might be interesting. Okay, we have 5-day beams, but 5-day is a multiplicity of 1. So that's my rough explanation why 1 day might work. Also, each day cannot be the same, because if you have all the days the same, I mean in terms of asymmetry, then your T0 sensitivity would not be visible. First of all, you would see 5 extrema within a beam, not just 1. So it looks like within a 5-day beam, we have one special day where we have asymmetry or something like that. Not each day for sure. And now we go to periodograms. So basically, this is inspired by Konstantin Zeutas and Marius. This is their idea and also Dimitri Butker leader of the GNOME project. This is their idea to connect the cosmo-seismic effect with dark matter stream. And if you think of a dark matter stream, and if you imagine certain arrival direction related to the stars, then you might ask whether you would see a periodicity related to sidereal day. Sidereal day is a full rotation of the Earth with respect to the stars. It is slightly less than 24 hours. To be sharp, 24 hours without 236 seconds. So 4 minutes less. And you see a periodogram again, a special period of time, which corresponds to our maximum of cosmo-seismic correlations. You see a dominant periodicity at 24, which is 1 day. It's in days here. And you see some family or other lines which seem to be significant. And you compare cosmic ray, observable, like in the article, absolute value of changes, bin to bin, and earthquake magnitude sum. But this looks similarly for number of earthquakes. So here is the region of the sidereal day frequency. On the right, you have a zoom. And especially in case of earthquakes, you have a very sharp correspondence, very sharp. And of course, uncertainty here must play a role, but I'm only highlighting that there is something near sidereal day periodicity. And I'm also telling you that it is, again, heavily dependent on time. So you have a special period of time here, and the picture might be completely different, including this major peak here at another period of time. I will demonstrate this using earthquake data. So here you see only earthquake data. Again, the threshold is larger or equal to 4. Big windows like in the article, and you see only two-dimensional picture, where in red you see the amplitude of periodicity at 24 hours. In blue, you see sidereal day periodicity, and in pink, you see the between. So you see 3 periodicities here, and you see something really big, amazing, 2 big, amazing peaks after the year 2000, which is at 0. But these are 2 peaks, so there is a valley here. It's really minimum here, so nothing here. But nothing means 4.5 years. So for 4.5 years, there was no leading 24-hour asymmetry. And you have a zoom here. At that time, you see that at that time, sidereal day periodicity dominates. And what is even more interesting, the strange periodicity in sidereal day periodicity amplitude. So it's a periodicity in periodicity. Very regular. One can fit some period. Thanks to a student, we can say that roughly it's 400 days. So not 1 year, for sure. And just a speculation, does it have any connection with Jupiter and Earth synod? But what I want to stress right now, it's only the evolution in time of periodicities around 24 hours. And to give you even a stranger picture, I show this 3-dimensional plot where you have frequencies on Y and time on X. Again, big windows, some sliding steps. And please note how the periodicity, 24-hour periodicity evolves in time. So here you have one of the 2 big peaks. Here is the other peak. And here you have, but it's not nothing. It's not that no periodicity is there. It's like it's split into 2 channels. 2 channels at the same time, maybe here. Okay, and then reconnect. What's that? How gravitational behavior could be so dynamic to produce periodicities not sharply at 24 hours, but around. And you also see a zoom related to sidereal day periodicity. on the right one zoom, and on the lower panel another. So this is not convincing in terms of historical evolution as well. So you do not have this sidereal day periodicity present at all times, for sure. And if you see it, it's again evolving. So it's around, not sharply at sidereal day, but something around sidereal day. And I want to finish with some support from literature. So as I have already mentioned, and I'm glad that Marios is here. Marios is a close collaborator of Konstantin Ziotas, who is the main proponent of dark matter stream scenario. So such a stream could be focused by massive objects in our solar system, which might produce effects and different periodicities. So that's clear. And what I can add, so if this dark matter is super heavy, we have scenarios of super heavy dark matter which decays or annihilates to produce secondary particles observable with standard means. So it means that we might see effects in cosmic radiation associated with some gravitational effects, if only we assume that this focusing might be that strong that induces really a seismic effect. And here is the work that explains how this focusing might look like. And they say that it might be even orders of magnitude focusing of dark matter streams. And another article, if we suspect sensitivity to magnetism due to this 24-hour dominance, why not to admit that dark matter might be charged? And we have a scenario. I've invited Professor Meissner. I'm not sure if he's connected. Maybe he can comment. Charged dark matter, super heavy dark matter. So this is what we want, actually. I'm not saying that we are confirming this, but we seem to have an effect which implies existence of some unknown factor which is acting at least in two ways, gravitationally and magnetically. And another very interesting result that supports our view, pointed out by Brian McBreen, who is following the literature and sharing the interesting papers. So there is it's a preprint. Okay, maybe it will not go through the review, but still, if this is confirmed, what we have is a space weather condition 1 million kilometers above Earth in a Lagrange point 1, correlated with radon emission on Earth at one location. You see, radon emission or decay in this case, excess for sure, correlated with conditions far away. So radon is also known, as we know, to be associated with the occurrence of earthquakes. So could it support our view that the solar activity or conditions around the sun, to be more specific, conditions around the sun could affect the processes associated with earthquakes? So it's not necessarily that maybe, as they propose ultralight dark matter scenario to explain this. So ultralight, okay, who knows? But something unexplained for sure. Maybe it's not as we suppose that some processes in the rocks, the stressing of the rocks being that precedes earthquakes is inducing the or enlarges radon concentration, and then we can use it as a precursor indication. Maybe it's another way. Maybe it's an external impact that induces both radon emission, decay, concentration, and earthquakes. So maybe there is not necessarily a clear causal relation between radon and earthquakes. Actually, I was talking to an expert, and it's not very clear. Sometimes he said this radon feature occurs after the earthquake only. So does not exclude this prediction power, of course, but this is also consistent with another explanation. And last but not least, an article, now regular article, where the authors report of something similar, dominant diurnal period in earthquakes in Japan with the no presence or not visible presence of lunar period. Dominant diurnal period, and they openly say that it is unexplained and it might point to a new window, new physical mechanism that produces earthquakes. But if this is 24 hours, and if we suspect it's not gravity, then what? Maybe we should begin to revisit our heliospheric education. So this is the heliospheric current sheet, which is a largest structure in the solar system. It is very thin, relatively. And this is related with the solar magnetic field. Sun is rotating differentially, so different latitudes with different speeds. And then the magnetic field rotates as well. And if there are charged particles around, they feel it, and they travel with this structure. So we can feel it. We can tell when we meet heliospheric current sheet, and it happens with surprisingly similar periodicities, which we also see in the data. Also, Marios sees this, and there's some literature, I suppose, around lunar period. Yes, but also this is corresponding to so-called Carrington rate rotation related with solar rotation. 27.25 days is Carrington rotation, and 27.32 is lunar rotation. But if we have two charges of our hypothetical dark matter, maybe we have similar structure composed not only by plasma as we know it, but maybe some other medium, and maybe not only one rotation direction. If we have different charges, it should rotate in the opposite direction. So maybe the situation is even more complex. Maybe our interpretation could really be open also for really crazy scenarios, which are represented by the graphics from my starting slide. And I'm leaving you with the consequences. If we are really looking at something big, this might offer breakthroughs not only in the foundations of physics. It might also be a significant chance for humanity in terms of predicting earthquakes sharply, because if we have this dark matter really coming and hitting us and Earth is shaking, and if it also emits radiation on the way, which we see in the form of the cosmo-seismic correlation, then we should, in principle, to be able to track these excesses of radiation with standard means like our global network of sensors. We should be able to track the upcoming heat, like asteroids, which are followed by astronomers, and they know the asteroid is on the way and it will hit us tomorrow at 10. So this is similar. Moreover, if we have a dark matter stream around, we should revisit all the climate change models, because none of the models considers dark matter stream. And it might bring energy. If it is capable of shaking Earth, it should also be connected with some temperature effects. So that's my final slide.
Okay, so let us thank our speaker for an insightful talk. First, and then I encourage you to ask some questions, because there is definitely much to speak about. Jerzy, please.
Could you please go back to this slide where was those binning and shifting time of the data? Okay, so there is this DCRI. As I understand it, this is just like a difference between the two bins. Absolute difference. So is it, maybe I missed it, is it sensitive to the width of the bin? So if you change it,
So the value in this approach consists of cosmic radiation within 10 days, because you need to compare two bins.
okay. So does it drastically, change the results if you don't have bins of 5 days, but 3 days or 6 days?
We have investigated that, of course, and yes, the drastic changes are there. Even if you only slightly change the bin size, like I've shown here. Yeah, so if you only change the bin size by 1 per mil, your change might be drastic. So this is the Oulu site. The 5-day bins at best gives 10 to minus 8 probability distribution function. So 6 orders of magnitude in significance if you only change the bin size by a very small fraction. So yes, this is a very, very interesting parameter. And I would say we are confident, I'm confident it's not a technical effect. We can keep on checking, of course, but if we admit the thought that it is a real effect, then we should try to start to think what could be the physics behind. What could be the physics behind such a sensitivity? So there are many questions related with timing. So bin size is one of them.
Maybe one more question or suggestion. Have you tried like completely different because this is like a observable, this DCR, maybe not a modulus or just because
yes, I did many times, many ways. That is why I highlighted the manipulation part. So many trials and then something, a prescription, which then was applied to some other region of the data. But for sure, the number of possibilities is very large, and we should investigate. Work is going on. Everybody is welcome to try. Of course, it's better not to try blindly. It's better to have some hypotheses in mind. So, for instance, we are maybe close to that. If this periodicities around 24 hours are going to be confirmed, that it's easy to imagine a quick test that we might apply just by subtracting certain parts of the data where we see the asymmetry in earthquakes and compare the cosmo-seismic outcome. This can be confirmed quickly at this point. I hope to do it soon. Then we might have the technical explanation, but still, technical explanation is only which kind of signal produces what we see, and we then still need to understand what is behind this signal, right? So we seem to have this kind of signal, which is periodic, and in earthquakes it looks like that. It changes in time. And now what is producing this signal? So now we begin to think about physics. This is unexplained. This asymmetry, as I said in the literature, so if you don't believe me, you might believe another author. This is unexplained and seems to be related with the cosmo-seismic effect.
And those are still like a global number of earthquakes, yes? Not local. Maybe,
yes, exactly.
Maybe we could like have a region.
I've tried, again, not reporting here, really narrow locations. So it's another chapter of the analysis. Presently, I call it 0.5 hemispherical differences. So of course you can identify locations on the Earth or regions or curves, edges, tectonic edges, where you have large seismic activity, and then you might see which regions produce which asymmetry, right? So it's not like every region produces the same asymmetry, but you might identify a hemisphere which is dominant in this picture. And then you might again follow the evolution, and it turns out that this is evolving very dramatically even within 24 hours. So you might compare the same hemisphere, so the same set of locations, wait 12 hours, and you have completely different number. So this is again pointing to some solar role. You have the slides in the backup if you want. You can check and we can discuss.
Okay, thank you.
Thank you, Jerzy. Thank you, Piotr. Any more questions from the audience?
Marius.
Yes, maybe just a comment. Thanks very much, Piotr, for the very nice presentation. I think all these results are very, very interesting, actually. So I have 2 points actually to make. One comment, just to highlight that there have been other precursors that have been found also in the literature before and that we have also explored. One of them, which is significant and actually enhances this probability of having something coming from the outside, as like the streaming dark matter case, is the total electron content of the ionosphere. So if you take the total ionization of the ionosphere, you can see that, for example, what we have seen is maybe 30 days before the very large earthquakes, this increases dramatically, and then it reaches a peak when the earthquake is happening, the big earthquakes are happening, and then it goes back down. And then there have been also literature, people have been looking at it locally as well. So this is also another precursor showing like some sort of downwards propagating signature, let's say, of something which is coming from above, from outside the Earth. And then you see also this kind of all this kind of phenomena. The other point that I wanted to make actually is with regard to the magnitude, which is something which is the magnitude of the earthquakes, I mean, which is something which is tricky and which should be very careful on our choices, is that if you take a small magnitude, you inevitably consider also aftershocks of earthquakes. So, you know, we know that when you have a very big earthquake, for example, you also have many, maybe 40 or 50 smaller aftershocks. And this means that if you take many of these, your sample might not follow, for example, Poisson statistics. So this is some point that I was also trying to investigate some time ago. So this is something to keep in mind for the future research.
Yes, thank you. So the second remark, I absolutely agree. But there is a price you pay when you focus on larger magnitudes, of course, lower statistics, right?
Of course.
With lowering the threshold, we receive interesting outcome. Of course, we have to be aware. I have said this, that it's not Poissonian anymore.
Exactly.
If you consider time evolution, that is maybe an important factor that increases the confidence, because if your result is polluted by aftershocks, then you might have single big events which change everything. But if you have a continuous, gradual, and sharp increase of the daily asymmetry, say in earthquakes, within some narrow period of time, like 5 years, which is a distinct period in the whole history, as I have shown, then it does not really it's not really compatible with the high role of aftershocks. I mean, the smoothness of such a increasing curve is an argument that the asymmetry is really significant independently on the lowering the threshold. But I fully agree.
No, I also agree with you. Yes.
It must be investigated. Another thing we have in mind and on the list, infinite list of to do related with analysis, is the differential approach to magnitudes. Maybe there is only a certain range of magnitudes which is producing, or maybe which dominates the effect. So many things, many topics.
Yeah, it's a good point. Yes.
PhD, PhD topics. So if young colleagues are listening, you're welcome to build your career on that.
I agree completely. We need more PhD students.
Any more people who want to ask our speaker? Okay, it looks like we are done with this topic. Thank you, Piotr.
Thank you.